Greetings to everyone. This is the first presentation for design and analysis of algorithms. Let's have a look at the element distinctness problem first. The problem asks that if we are given an array of n numbers, are all the n numbers distinct? So we can say that if the input is an array of numbers, let's say x of n elements, the output should be yes if all the elements in X are distinct, and no if at least two elements are equal, that is all of the elements are not distinct. So the output should be a no. The question we ask here is, can we design an algorithm that runs faster than big O of n log n, that is in small o of n log n time? And the answer to this question is unfortunately no. It's not possible to design such algorithm because the lower bound of the time complexity of this algorithm is n log n. Let's prove this claim. So yeah, this proof will be in 4 steps basically. We assume here that the viewer is aware of the concept of decision trees, and we consider a decision tree model of the comparison type. So the only operations allowed are comparisons. So here's the outline of the steps for the proof. The first one is interpretation using n-dimensional geometry. Then we'll look at connectivity or convexity of a region. Then the third part is distinct permutations and distinct leaves, and then we'll perform the final step, which brings everything together. Okay, so let's move on to the first part, interpretation using n-dimensional geometry. So what we'll do here is we'll interpret x, which is an input to the distinctness problem, as a point in n-dimensional space within a unit cube. That is, all the elements of the array X, or the n elements, will be between 0 to 1, let's say, and we can assume that these n numbers, or these n elements, are n coordinates of a point inside an n cube. For example, if n is equal to 2, we can see in the figure to the left, it can be visualized as a point inside a unit square, as it has two numbers, so it can have two coordinates. And we see that if it lies in the green region, in the region highlighted by green, the output of the distinctness problem is yes, because x1 is not equal to x2. The only place where x1 will be equal to x2 will be on the red line, because at that point x and y coordinates would be equal, and thus the output of the distinctness problem would be a no. Okay, so the interpretation of the input can be done in this way using n-dimensional geometry. Moving further, let's explore connectivity of a region, and with that the convexity of a region. Okay, so first let's define a region R of L as R of L will be the instances for which leaf L is reached on the execution in a decision tree. That means that for any input X, if the execution of the decision tree arrives at a leaf L, that instance X will belong to the region RL. Thus, for every X, all the conditions along the path to L must be satisfied if it belongs to RL. Of course, if it reaches the leaf L starting from the root, every condition along the path must be satisfied. That's how it reaches L. Okay, so we'll keep this in mind, like RL is such region. Okay, next we can define connectivity. It's a simple concept. For a region R, and points x and y belonging to R, there exists a path from x to y which passes entirely through R. On the similar lines, a convexity is a more special case of connectivity, which is that if the same region R and the 2 points x and y belong to R, then there exists a straight line path from x to y which passes entirely through R. So if we take any 2 points in a region and draw a straight line from the first point to the second point, that entire line must lie within that region R. And of course, as we see that connectivity is a generalized case of convexity, therefore it follows that if a region is convex, then it has to be connected. Okay. So, okay, let's consider two inputs to the distinctness problem. X1, X2, X3, Xn will form X, and Y1, Y2, Y3 till Yn will form Y. Both have n elements and both belong to RL for some leaf L, let's say. Thus, when X is executed uh, in the decision tree, L will be reached. When Y is executed, similarly, L will be reached. Now, let's define Z to be another input such that Zi is equal to lambda xi plus 1 minus lambda yi for all I, which means that every element in Z has this particular relation with the corresponding elements of x and y. Now, it is obvious geometrically that if lambda is between 0 to 1, Z lies on a straight line between x and y. And if it does not, if it's outside those bounds, it will lie on the straight line but still outside x and y. As Z, all the elements of Z are linear combinations of the corresponding elements in x and y. So now we know like uh, both of them, both the points x and y reach L in the decision tree. Therefore, x and y belong to RL. At some arbitrary step in the decision tree, let the label be ij, and without the loss of generality, let's take that the branch which is taken at that step is the less than branch. As this is a comparison model decision tree, there are only 3 branches, less than, equal to, greater than. So let's say that less than branch is taken at that step, and therefore xi will be less than xj and yi will be less than yj, right? All right. So if we multiply uh, the corresponding respective equations by lambda and 1 minus lambda and add them, we see that lambda of xi plus 1 minus lambda of yi is less than lambda of xj plus 1 minus lambda into yj. This implies that zi is less than zj for all ij, because that's how z is defined, and thus this branch is taken by z at the exact same step in the decision tree. Now, this can be proved for all the branches. This will be true for all the branches. Thus, Z will also belong to RL, as it follows the exact same path which x and y take and reach L. And as Z is any point on the straight line between x and y, the entire straight line path lies in the same region, because any point on the path lies in that region. Thus, the entire straight line path will belong to RL, and thus, as x and y also belong to RL, RL is convex, as the definition of convexity goes. And we have already established that if RL is convex, RL has to be connected. So RL is connected. This is a very important result which will aid us in our further exploration. We can also visualize this with some geometric intuition. Okay. For this example, we'll consider n is equal to 3. So there are 3 elements in the input. For x, it will be x1, x2, and x3. And all the inputs lie in a unit cube as per our interpretation. So at the first step, let's say if the label is 1 and 3 and the branch taken is the greater than branch, let's say for example. So what will that result in? It will result in all the points where x1 is greater than x3, which corresponds to an entire region where x1 is greater than x3. And what region will that be? That region will be everything which is in front of that highlighted plane, which we can see, the diagonal plane. Thus what we see, that this step, taking one step, resulted in slicing of the greater region which was there initially. So every such step will result in further slicing of the region. And we know already that slicing maintains convexity. If we slice a convex region, the result will be also a convex region. And the unit cube is a convex region. Thus, as RL will be a region formed by multiple such slicings, RL will also be convex. And therefore, as RL is convex, it will also be connected. So we can see this geometrically as well, what we saw in the previous slide algebraically. Moving on to the third part, distinct permutations and distinct leaves. Okay, so let us consider an input x again of n elements, which contains all distinct elements as an input to the problem. As all the elements are distinct, the output of the distinctness problem will definitely be a yes. Let y be a different permutation of x. So it will have the same elements but in a different order. And as this is the case, all the elements are definitely distinct, and thus the output of the distinctness problem in this case will also be a yes. Now, let us assume that x and y belong to Rn. So what does this mean? That both of them reach the same yes leaf L. Of course, both of them will reach a yes leaf in the decision tree because the output of the problem will be a yes. And we are assuming here that both of them reach the same yes leaf L. Now, without the loss of generality, we can consider an X where all the elements are in ascending order, all the elements are distinct, and let's say they are in ascending order. Now, as Y is a different permutation of X, Y also cannot be completely sorted. Which of course, as you see, which will not make sense. If both of them are sorted, both of them would be the exact same permutation of the elements, as all the elements are distinct. So yeah, this means that there exists at least one pair of ij such that xi is less than xj and yi is greater than yj. And if we think about it, it will be true for any x and y, like we visualized by an example where x is sorted in ascending order, but it will be true for any x and y if you think about it. So now let's keep that in mind, and let's define a function f which takes the value of the ith and the jth elements of a particular input and subtracts them. So for any k, fk would be ki minus kj. Now we know that at some point there exists at least a pair ij where xi is less than xj and yi is greater than yj. So in that case, the value of the function f at x would be less than 0, and the value of the function f at y would be greater than 0. Now, this means that by the mean value theorem, there exists z, an input z, that belongs on a path from x to y such that the function value of z is 0. Of course, that's what the mean value theorem says. If you are going from a positive valued function to a negative value or vice versa, you are bound to hit 0 at some point. But what does this imply? This implies that there exists a z such that zi minus zj is 0, right? Because that's how the function f is defined. Fz is 0, so zi minus zj is 0. That is, zi is equal to zj. But what does this say? If zi is equal to zj, that means that in an input z, two elements are the same, which means that the input z is not distinct, which means that it will end on a no leaf, which means that it will not end on leaf L because L is a yes leaf, and thus Z does not belong to the region RL. But we know that RL is connected, and the path from X to Y passes entirely through RL. As RL is connected, the path from X to Y definitely passes entirely through RL. So all the points on that path will lie inside RL. As Z is a point on that path, it also has to lie inside RL. But what did we just see? That Z does not belong to RL. This is a contradiction. And as we reached a contradiction, that means that our assumption was wrong. What was our initial assumption? Our initial assumption was that X and Y, two different permutations of the same set of elements, reach the same yes leaf L, and thus both of them belong to RL. So this assumption is wrong, which means that X and Y, which are again, to reiterate, the different permutations of the same set of elements, must reach distinct yes leaves. So X and Y must reach distinct yes leaves. This is again a very important result. Now let's proceed. Now we come to the final step. We can wrap it all up. We have got everything we require. So let's say for an input X of n elements, it has all distinct elements. Let's say for such X, there are n factorial possible permutations for input to the distinctness problem. Because there are n elements in the array X, we can arrange it in n factorial ways, and thus there would be n factorial possible inputs. And as all the elements are distinct, each permutation reaches a distinct yes leaf, as we proved in the earlier slide. And if each permutation reaches a distinct yes leaf and there are n factorial possible inputs, there must be at least n factorial yes leaves in the decision tree. And if there are n factorial leaves in the decision tree, we know that time complexity is at least the height of the decision tree, which is log of n factorial, which is n log n. So we have proved that the lower bound for any algorithm which solves the distinctness problem is at least n log n. We cannot have any algorithm which does better than this, and ultimately, to reiterate the statement, the lower bound for the distinctness problem is n log n. Thank you.